if you need to go back and look at that. So I'll be checking your pages here on Tuesday when we come back, and just to make sure that you have everything filled in, what we're doing. So the biggest thing to remember is that you have your own set of data numbers that you took when we did this lab here. If you were at home, you use these data numbers that I wrote down. If you were not online yesterday, if you were not at school yesterday, then you're going to want to have these numbers as well. So I am on page 8 of your packet. All right. So we took the mass of one washer here and 3 washers here. Remember that these are going to be in grams. And so we're going to have to actually convert these to kilograms, because when we do calculations, like for any of our energy problems, all of our masses have been in kilograms, right? Everything's been in kilograms. So that's what I want to start with first. Is we got some space in that in the table there, in where it says mass. We're going to do a quick conversion of this to kilograms. So in order to do that, we're going to bring back a favorite of ours, which was that picket fence method. Okay, so what I want you to do is up here where you have your first mass, for the data that I have, it's 6.3. Your mass may not be exactly the same, because I have different size washers, and whatnot. Your mass could be a little bit different. So as I'm starting this out, I want to make that line here like this, with this picket fence line right here. Okay, remember, I don't put anything there. And so if I have grams up there, I want grams right here. I'm going to go ahead and zoom in on this part so you guys can see this. Okay, so I have grams up there, I have grams down here, so I want to go to kilograms. And as far as when I look at grams versus kilograms, a kilogram is bigger, and there are 1,000 grams in a kilogram. Kilo means 1,000. Okay. So basically, we're going to take this number here, I have 6.3, and we're going to be dividing it by 1,000. Okay. So take your mass for data table 1, and you're going to divide it by 1,000. Another way that you can look at this is that you're going to be moving your decimal point back 3 spots. Okay, so 1, 2, 3, and then you just fill this in with zeros. So either way, if you actually do the division or if you just move decimal places, again, 6.3 divided by 1,000 gives me this. Oh, I did 100. Sorry, excuse me. 6.3 divided by 1,000 equals 0.0063, or whatever number you had. Don't forget the 3. Take that 3 along. Okay, so we're going to put kg there. Okay, so that'll save us a step when we get down to number 1, is converting this to kilograms right away. All right, now we're going to do the same thing for the mass in data table 2. All right, so I'm not going to show all the steps here just because it gets kind of mucky, but basically we're just going to take 21.9, go ahead and make a slash here for divided by 1,000, right? So again, your number may not be 21.9. You got to use whatever you have written down. But 21.9 divided by 1,000 should give me 0.0219. So no matter what your number was, everybody should be right around these numbers. Okay. And don't forget to bring all the numbers with it. So you should have 0.0 and then 3 numbers after that, unless yours was actually 21.0. Just have the 2 numbers there, but same place values. kg. Sorry, my ear thing's falling out. Okay. So we are, like I said, the whole point of doing that was to convert to kilograms because I need kilograms later on here. Ready? Actually, not later on, right now. All right, if there's no major questions on that, I'm going to move on to question number 1. Zoom myself out a little bit here. All right. So question number 1 says, what type of energy did the pendulum have before person number 2 let go? So person number 2 was the person that was letting go of the pendulum for each of your swings. Excuse me. And so we want to first answer this question here. So what type of energy do they have before the person number 2 let them go? So they're holding it, right? It's above the surface of the earth. It's got a height. It has a mass. That looks to me, since it's not moving, like it's going to be GPE, okay? So GPE is the type of energy that I have right before that person lets them go. So now it's asking me to calculate this GPE for both pendulums. So I need to do 2 calculations here. They're both going to be set up exactly the same. All right, I'm going to be using different numbers though for my data. Sorry, screen went too far on me here. Okay. Now, this is what I suggest doing is that take this whole space that you have for number 1 and split it in half. Okay. Put a line down the middle here and split that in half. And over on this side, just off to the corner, put the number 1 with a circle. That's going to represent like data table 1 or the first trial that we did with the 1 washer. And then a number 2 over here, which represents data table number 2 with the 3 washers. Okay. So if you wanted to put 3 washers as a reminder here, and 1 washer as a reminder here, you can. So if I want to calculate GPE, I have 4, variables that are involved in that. So just like we've been practicing and doing, we're going to write all of those out. So my equation is GPE equals ham, right? So ham, go ahead and zoom in a little bit here. This thing's so touchy. This goes right by all the time. Okay. So GPE, H, A, and M. Now I can actually do the same thing right away over here under number 2. So GPE, because I'm going to use the same equation. H equals A equals M equals. Okay. So write small, because we got lots of info in here. Okay. So when I look at data table 1, let's do this calculation first. I know that my GPE is what I need. So that's going to get my question mark, right? My height is the height that it was dropped from. Now be careful here because some people in like 5th hour tried to write 50 centimeters down. But remember that we need to use meters because that is the unit that's involved in this. So we need to use meters. So 50 centimeters is the same thing as 0.5 meters. Okay, so 0.5 is the number that we'll use for our height. That's 50 centimeters. Okay. Acceleration. is always 9.8 meters per second squared. I'm not putting my units over here on the side because I want to leave enough room. And then my mass, all right, remember this was the 6.3 grams, is for me, but I want to use the number that we converted it to. So you got to go back up here and look at this number right here and use that one. Make sure that you have and transfer all your zeros correctly. Okay, don't miss one. So 0.0063. So again, everybody will have 0.5, everybody will have 9.8, but your M may be different. So then the equation that we use, HAM. So this is a nice easy one. We're just going to plug these in. I'll put parentheses around them. 9.8 goes in. 0.0063 goes in. So all of these just get multiplied by each other. Okay, nice easy calculation for us there. So I would need to take 0.5 times 9.8. Again, everybody will have that. And then whatever you have for your mass, 0.0063 for me. All right, so you're going to get a small number, and I'll discuss why that's going to be true here in a moment. What I would like to do is have us, everybody, just go out to 4 decimal places. So this is the number that I get here. So 4 decimal places would be 1, 2, 3, 4. So I'm going to stop right there. But I'm going to go ahead and round it. So that would be 0.0309. Again, your calculation will differ because your mass might be slightly different. If your mass was exactly the same as mine, 6.3 grams, and this is exactly how yours will look. The only thing I'm missing now is my units. And since I was calculating for GPE, my units are joules. So go ahead and put a circle or a box around it. Now, usually when we calculate problems for energy or for joules, we're sort of used to seeing like maybe numbers in like the hundreds for joules or thousands maybe even, but it should make sense that this number is small because I'm talking about a washer, like that tiny, I mean, you can hold it in your hand and you can tell that it doesn't have a lot of mass. Look at how little your mass is, especially compared to kilograms. All right. Another thing that's making this number small is your height. All right. We're usually talking about dropping stuff from at least like a couple meters, right? This is only 0.5 meters. So it makes sense that this number is going to be small. A washer drop from a half a meter stick is not going to have a ton of energy. All right. So now we're going to go ahead and do the same thing for number 2. Now, the only thing that's different here is my mass. Everything else is the same. My GP is my question mark. My height is 0.5. My acceleration is 9.8. But this time, use the mass that we converted to in data table number 2. So it'll be this number right here, your second data table. Okay. So for me, that was 0.0219. Again, kilograms, but I'm not going to worry about my units in here just for space. All right, so GPE equals AM equals 0.5 times 9.8, 0.0219. Okay. So same numbers essentially, same units, same multiplication order. It's just my mass is different. So we have 0.5 times 9.8 times, for me, 0.0219. Okay. So for me, I get 0.1073. Again, your number might vary slightly, but you should still, it should still be low like this. And then I'm going to go to 4 decimal places. So that's 7.3. And this is joules once again. All right, so I'll leave this up here for a sec so you can get that down. Sometimes my decimal points always kind of disappear. All right, so again, this one is larger than the other, but it still is not like a crazy big difference, or, a crazy big number, because again, it's more mass, but it's still fairly small in terms of, like, when we use examples about, dropping a ball or a person or a car, those are usually much more massive than a few washers. All righty. So now we should be able to answer question number 2. I'm going to zoom out a little bit for this. So question number 2 says, referring to your calculations from number 1, which pendulum had more initial energy? Explain why this makes sense. So the washer, or the pendulum that had more initial energy, was the one with 3 washers. Okay, so the 3 washer pendulum had more initial energy. And then let's think about why that is. Why is this number higher than this number? Okay, well, look at the equations. Your height is the same, your acceleration is the same. The only thing that's different is your mass. Okay, the one with 3 washers is roughly about 3 times as heavy, all right, than your first data table that we did. So that makes no sense, because you're multiplying all these, that it's going to have more mass. So the 3 washer pendulum had more initial energy because it has 3 times the mass. Because it has 3 times the mass. Right. My plan is to work up to number 6, maybe. You don't have to do any more calculations, so they're just answers here now. All right, so number 3 says, how could we have made both pendulums have more energy, more initial energy? Well, I can't mess with the acceleration because that's just due to gravity, okay? I already changed my mass, so, I mean, that's kind of something I already did. But the only other thing that I could do if I wanted to keep my masses like the same, I could increase my height. Any increase in your height is an increase in your h, which, anytime you multiply this by something bigger than 0.5, it's going to make it higher, okay? So you could have made both of these have higher initial energy by giving them greater heights, okay? So giving them greater heights or increasing the heights, right? Again, you can't really mess with the acceleration. The mass was already changed. I mean, I suppose you could change both of them again, but you know, that's not really answering the question here. We want changing the height would also change both pendulums. Okay, so increasing the height will make it bigger, make the total energy bigger. All right. So looking at question 4 on the top of page 9, says what type of energy did the pendulum have after person number 2 let go? Explain how you know. So after person number 2 let go, then the washers are moving. So this turns into kinetic energy. Okay, because the washer is moving. It has a speed now, okay? It's in motion, it's moving, that's kinetic energy. Number 5 is asking when in the pendulum swing should it have the most gravitational potential energy? Explain how we know and draw a picture. So I'm going to start by drawing the picture here. So I'm going to put this kind of off to the side so I can write my answer over there. Here's my ruler, okay? And think about where is the highest potential energy in our system. Potential energy happens when it's above, you know, a height and has dropped. So that is going to be like right out here. So here's my little washer. Here's the string. There's where the energy, the GP is going to be the highest. Okay. So again, we're in the swing at the top because it has the largest height. Okay. So the top of the swing is where it's going to have, when you're holding it straight out like that, that's where it's going to have the largest height. And it's not moving. Okay, last one here that we'll do today. When in the pendulum swing should it have the most kinetic energy? This would be at the bottom of the swing, okay? So when you draw your picture, washer, that's when it'll have the most kinetic energy. So at the bottom, because that's where speed is highest. And we saw that when we did the example of that skateboarder, right? She always reached her maximum speed at the very bottom of the ramp, okay? So the same ideas translate to this right here. All right. So as soon as you have that done, you are free to go. You don't have to do anything else as far as the questions go. We'll continue on them on Tuesday. So have a good weekend, but take your time and get this written down first. So